Hi everyone, welcome to another video for research design and analysis. In today's video we're going to be talking about strategies for post-hoc tests and thinking about what we need to do when we're running a factorial ANOVA and we have multiple levels of a variable. So we might be getting a statistically significant main effect or a statistically significant interaction, and that tells us that there are differences among our groups, but we don't know precisely where those differences lie, so we need to follow up those omnibus F tests with individual paired comparisons to understand which groups are different from which other groups. So first, let's consider a 2x3 factorial ANOVA example. So this is a hypothetical study where we're looking at the combined effects of psychotherapy and some kind of pharmaceutical treatment on depressive symptoms. So our symptoms are captured by this mood score where positive numbers indicate fewer symptoms. So essentially higher is better here. We're looking at groups of people who were randomly assigned to receive either drug A, drug B, or the placebo. And we're also randomly either assigned to a control condition where they received no psychotherapy or an active treatment condition where they received psychotherapy while they were on these medications. So we ultimately end up with 6 groups in this study, and we can look at a main effect of psychotherapy, a main effect of drug, and the interaction between drug and psychotherapy. So if we analyze these data, what we would get is an ANOVA table something like this. We've talked about these analysis of variance tables in previous examples, but ultimately we can get a main effect of psychotherapy and the variance explained by that, calculate an omnibus F test and a p-value. Right, the main effect of drug, get the variance explained by that, calculate an omnibus F test and a p-value. And similarly for the drug by psychotherapy interaction, we can get the variance explained there, the omnibus F test and the p-value. Now in this example, right, we happen to have both main effects and an interaction that are statistically significant, but the exact way you're going to approach your post-hoc tests depends on what is statistically significant in your data. In this example, because the interaction is significant, that's going to be most important. But let's actually look at each of these main effects in turn. So for instance, if just the effect of psychotherapy had been significant and drug and the interaction were not statistically significant, that's a pretty easy situation to unpack because the main effect of psychotherapy is telling you, on average across the different levels of your drug, there is an effect of psychotherapy. And psychotherapy only has 2 conditions. So there's not a need to even do a post-hoc test here because we can just see, well, which condition is scoring higher. We know that those 2 conditions are statistically different. If it's only a single degree of freedom test, because we only have 2 groups to compare, we don't really have to do a post-hoc test. The F test tells us that there are differences among these groups, right? Or there's variance explained by what group you're in. And there's only 2 groups, so we know where that difference must be. Right? Conceptually, we can think about this as averaging across the levels of the drug and comparing everyone who was in the control condition to everyone who was in the treatment condition. And you might present a figure, without these boxes drawn over the top, but you might present a figure showing all 6 of your data points. But if the main effect was the only thing that was statistically significant, you would also be justified in just collapsing across levels of drug and showing psychotherapy. Because in essence, if psychotherapy was the only thing that was reliable, we don't necessarily have a great reason for showing the other effects. You might still show it for illustrative purposes, but this main effect of psychotherapy would directly map onto a comparison between everyone who was in the control condition compared to everyone who was in the treatment condition. And we can see then that people who were in the treatment condition did significantly better, right, in terms of their mood scores following psychotherapy. Similarly, if just the main effect of drug was significant, and now let's pretend like the main effect of psychotherapy was not significant and the interaction was not significant, we would have to unpack where the differences are between our different drugs. Now, the main effect of drug has 2 degrees of freedom, so this is a situation where we would have to do some number of post-hoc tests following the statistically significant omnibus test. Because again, the omnibus F test just tells us that significant variance is explained by which drug you received. The other way to kind of simpler way to say that would be the drug you received made a difference. But which one made a difference, right? We don't know if drug A was different from drug B, if drug B was different from placebo, or if drug A was different from placebo. So in order to unpack this main effect of drug, we would have to conduct at least, probably 3 different post-hoc tests where we compare all of those different conditions to each other. And again, conceptually, right, we're averaging across the groups who received the psychotherapy conditions in order to compare drug A to drug B and placebo. So in a figure, right, you could show all 6 of these groups at once, but what this main effect would really be looking at is ignoring psychotherapy. Was there an effect of your drug, and were there any statistically significant differences between these 3 groups? And you would need to do 3 post-hoc tests in order to determine which groups were statistically different from each other. And they might all be, maybe only one of them is different, right? From the F test alone, we don't actually know. We would have to go in and perform a series of post-hoc t-tests in order to compare these different groups. Now, in this specific example, however, we have a statistically significant drug by psychotherapy interaction. So that interaction supersedes the main effects, right? Because the main effect of psychotherapy tells us, on average across drug, this is the effect of psychotherapy. And the main effect of drug says, on average across psychotherapy, this is the effect of drug. But the interaction is telling us that looking at things on average isn't the full picture, because the effectiveness of the drug depends on whether you're receiving psychotherapy or not. So we really need to consider the effects of these things at the same time, because the effect of one of our variables depends on the level of the other variable. Now this creates a tricky situation, and this is only a two-way interaction, so you could have a more complicated scenario, but in this two-way interaction we have a lot of different things that can be compared, and we have to decide exactly what comparisons we want to make, because we know that the effect of drug depends on whether you receive psychotherapy, or conversely we could say that the effect of psychotherapy depends on what drug you're receiving. So if we get the statistically significant interaction, we have a lot of different groups that we could potentially compare. And there are different strategies and approaches for how to do these post hoc tests in the wake of a statistically significant interaction. Now, this is where post hoc testing becomes a very contextual question. So I want to talk about some general strategies in terms of which post hoc tests you might want to do, and then some general strategies for correcting from running multiple tests. But the exact strategy that you have for conducting a post hoc test will depend a lot on how many comparisons you're running and what is the relative cost of making a type 1 error. That is, how bad is it if you make a false positive? So let's talk about 2 different post hoc testing strategies first, and then we'll get into corrections for multiple comparisons. But I'm going to talk specifically about pairwise comparisons, which is a pretty standard strategy that a lot of statistical programs will provide. And then I'm going to talk about simple effects tests, which is kind of an easy heuristic that potentially allows you to run fewer tests relative to the full pairwise comparisons method. And the exact one of these that you do, or if you adopt a different strategy, again, might depend slightly on your research question. So let's look at pairwise comparisons first. The basic idea behind pairwise comparisons is that everything gets compared to everything else. So in the wake of this statistically significant interaction, if I ask for pairwise comparisons, which is the default in R, SPSS, in Jamovi, right? A lot of different stats programs will give you everything compared to everything. And that can be helpful. It is very informative because we're, comparing every group to every other group. So there's basically no stone left unturned in this pairwise comparison method. However, the cons here are that we're running a very high number of tests and that not all comparisons are necessarily meaningful. So for instance, meaningful comparisons might be, is there an effect of psychotherapy among people who took drug A, right? And is there an effect of psychotherapy among people who took drug B and in the placebo? Or among people, who were in the control condition, was there a difference between drug A and drug B? And was there a difference between drug A and placebo? So a lot of times, there are important questions that are getting asked here. But sometimes there are things that are less important, like control participants who took drug A being compared to treatment participants who took drug B. Well, there are 2 differences there. There's a difference in terms of the psychotherapy they received, and there's a difference in terms of the drug they received. So I actually kind of have 2 things that are different in that comparison, and it would be hard to attribute where the difference is coming from. Is it due to the psychotherapy? Is it due to the drug? If I'm making those comparisons. So pairwise comparisons can be very useful, but you have to be careful because you're running a very large number of tests, and not all of those comparisons will be things you're really interested in, depending on your exact research question. Again, sometimes they are. Sometimes you really want to know, and it might be helpful to compare these two groups, even though there are two things different about them. But from a hypothesis testing perspective, we're often not interested in every comparison we could possibly make, especially following an interaction. This might be a little more helpful as a strategy following a statistically significant main effect, but given a statistically significant interaction, a full or set of pairwise comparisons is not always the most helpful. So as an alternative strategy, we can conduct a series of what's known as simple effects tests. And the idea of a simple effect is that it's the effect of variable A at a particular level of variable B. So in order to do all the simple effects tests, we have to test variable A at every level of variable B. So for instance, we might want to know, is therapy effective across all levels of the drug variable? Well, at each level of drug, I could run a t-test comparing the treatment group to the control group and say, was psychotherapy effective if you got drug A, if you got drug B, and if you were on the placebo? And depending on my exact research question, that might be all the post-hoc tests that I really run. I just really want to know, is psychotherapy still effective across all these different drugs that people are receiving? However, that's not the only set of simple effects that we could calculate. We could also look at the simple effect of drug, which then would say, well, we want to compare all of the different drugs when people received psychotherapy, and we want to compare all of the different drugs when people were in the control condition, right? So the simple effects tests would require us to look at the effect of therapy at each level of drug. And then we could also look at the simple effect of drug and say, okay, at each level of therapy, was there an effective drug? And if you wanted to save yourself running 3 tests here, you could also conduct a one-way ANOVA for the effective drug at each level before jumping directly into these t-tests, right? So you could actually ask an omnibus F question here and say, well, was there a statistically significant F for the effective drug in psychotherapy, and was there a statistically significant F for the effective drug in the control group? Either of those things would be valid options, and adding in that kind of extra ANOVA step might save you a few tests. But given that we only had 3 drugs to compare, that's not too many, so I jumped right into basically running 3 different t-tests in the treatment condition and 3 different t-tests in the control condition. So by adding those 2 sets of tests together, we can ask a lot of meaningful questions while running fewer statistical tests than if we did the full set of pairwise comparisons. So this method of doing simple effects tests is a good way of answering things that are relevant to your hypotheses while saving yourself a few statistical tests that might not be the most interesting or the most informative. One of the cons of this method, however, is that not a lot of stats programs do this by default because it's a little bit harder to program. It depends a lot on exactly how many variables you have and what analyses you're running. So this usually requires you to subset your data on your own and say, okay, well, we'll look just at the drug A group, do a t-test for psychotherapy, just at the drug B group, do a t-test for drug B, right? Just at the placebo group, do a t-test for psychotherapy. So it might require a little more legwork on your end, but ultimately it gives you fewer statistical tests that you have to run, and often those statistical tests are going to be more meaningful than if you did the full set of pairwise comparisons. All right, so now we can talk about correcting for multiple comparisons, because regardless of the approach we take, post-hoc tests will always lead to multiple comparisons, right? So in this example where we did pairwise comparisons, there's 15 total tests that we run here if we want to compare everything to everything else, right? If you add up all those red lines, which each represent an independent sample's t-tests, there's 15 total tests. If we went the simple effects route, at a minimum, we'd be running 3 tests, like if we were only interested in the simple effect of psychotherapy. And at most, we'd be running 9 tests if we did both the simple effect of psychotherapy as the red lines and the simple effect of drug as the blue lines. So in either case, we're running multiple comparisons. We might just be running a lot in the fully pairwise example, or we might be running a small to large amount in the simple effects example. So how do we control our type 1 error rate when we need to run a large number of tests? Well, first, right, we should always avoid, well, I should say almost always avoid conducting individual comparisons unless the omnibus F test is statistically significant. If you have a really strong a priori reason for looking at a specific paired comparison, that's okay if you have that a priori comparison in mind from the beginning of your experiment through to the analysis. But in general, most of the time, we're unsure exactly where differences are going to lie, so we want to use the omnibus F test as kind of the first bar we have to get over in order to avoid false positives. After that, we can then adjust the alpha level for each of our individual post-hoc tests in order to control the type 1 error rate overall. And in this video, I'll talk about a couple different ways that we can approach that, focusing mostly on doing no correction for the alpha level, which is very liberal, or doing the Bonferroni correction for the alpha level, which tends to be very conservative. But you should know that there are a lot of different types of corrections and adjustments that you can make based on the relative costs of false positive versus false negative errors in your research. So first, let's talk about making no correction for multiple comparisons. So let's use this simple effect strategy, and let's assume that we're going to do all 9 tests. We're going to do both the simple effect of psychotherapy and we're going to do the simple effect of drug, right? So again, for all of these arrows, we're running a t-test, and each of those t-tests has its own type 1 error rate. If we just leave that type 1 error rate at 5%, right, each test has a 5% type 1 error rate. So the total type 1 error rate is going to be pretty high if we run 9 different tests. And specifically, you could figure this out by saying, okay, the total type 1 error rate is going to be 1 minus basically the probability of not making an error, right? Because alpha is the probability of making an error. So 1 minus alpha is the probability of not making error raised to the power of the number of comparisons you're making. So in this case, it's 1 minus 0.95 to the 9th, which means we have about a 37% chance of making an error here, right? At least one type 1 error here. So that's a pretty high type 1 error rate. So if we don't make any adjustment for multiple comparisons, 37% chance of a type 1 error is obviously much higher than a 5% chance of a type 1 error. So that's why we say that this is pretty liberal. Your total type 1 error rate is going to be a lot higher if you make no adjustment. However, type 1 errors aren't the only kind of errors that are a problem. We might also be worried about a type 2 error rate, right, or a false negative. So when you make a false positive and you declare something statistically significant when you really shouldn't, that can have some problems with it. But also if you declare something not statistically significant when in reality those two conditions were different, you might miss an important difference between two conditions. So no correction might actually be useful when the cost of a type 1 error, right, or the cost of a false positive is low, and the cost of a type 2 error, which is to say the cost of a false negative, is high. So in general, this kind of no correction, this very liberal and permissive attitude, is probably only going to be more important in early phases of exploratory research. You're trying to operationalize your research question, maybe decide what key variables are important, and basically if you find a statistically significant result, the next thing that's going to happen is another experiment where you probably try to replicate what you found. So if you're doing an early phase experiment and the next thing that's going to happen is just another experiment to basically say, do we get the same thing? This higher type 1 error rate might be acceptable. However, right, in a lot of situations, we're more concerned about type 1 errors than we are about type 2 errors. So for instance, if we're testing the efficacy of a drug or we're testing the efficacy of some sort of physical therapy treatment, we don't want to say that one thing is more effective than another thing and then be wrong. Because that could lead people to invest a lot of money and time and effort in that treatment when ultimately that treatment wasn't any better than, the current standard. So oftentimes type 1 errors will be a big concern, especially in later phases of research. So in those situations, we're definitely going to want to implement some kind of correction for multiple comparisons. And a very common one, but also a very conservative one, is the Bonferroni correction for multiple comparisons. Now, the nice thing about the Bonferroni correction is it's pretty easy to understand because all we do is divide the type 1 error rate by the total number of comparisons to get an adjusted alpha level. So alpha adjusted, indicated by that little tick mark there, is equal to our original alpha divided by the number of comparisons. So if our original alpha was 0.05, we divide it by the 9 comparisons that we're going to make here, our new alpha level is 0.0056, which means then the p-value for any of these individual t-tests over here has to be less than 0.0056 before we're willing to say that it's statistically significant. So that's a much higher standard of evidence, right, before we reject the null hypothesis. But the advantage of doing this then is across all of these different t-tests, now the total type 1 error rate is the original alpha, right? Across 9 different tests, if each test has an alpha level of 0.0056, then across all 9 tests, the risk of making a false positive is still only 5%. So this Bonferroni correction is nice in its simplicity, but the thing is it tends to be a pretty stringent way of controlling your type 1 error rate, especially as the number of tests you're running gets bigger. You can see we only had 9 different tests here, and already we're setting a pretty high bar for how different 2 things have to be before we're willing to declare them statistically different. So the Bonferroni correction is very conservative, and it's going to be most appropriate when the type 1 error rate is high and there are a low to moderate number of tests that you need to run. 9 isn't so bad for the Bonferroni correction, but you could imagine if we were doing some kind of neuroimaging study and we're looking at a whole bunch of different brain regions, we might be comparing hundreds of different regions, right? So if we're dividing now alpha by hundreds or thousands of different tests that we might want to compare, the adjusted alpha is going to become incredibly conservative. And now we're really cracking down on type 1 errors, but we might make a lot of type 2 errors, and we might have a lot of false negatives and miss things that we should otherwise be picking up on. The other thing to note here is that some stats programs actually adjust the p-value rather than adjusting the alpha level. So rather than doing alpha divided by the number of comparisons, they'll take the p-value observed for a given t-test and multiply that by the number of comparisons, capping it at a p-value of 1 to give you a p prime rather than an alpha prime. Now, mathematically, these are equivalent adjustments, but it's just something to look out for because some stats programs, right, rather than giving you an adjusted alpha level and then saying, okay, now look for p's that are less than that alpha, they will just adjust your p-value by multiplying it by the number of comparisons. So you're still looking for a p less than 0.05, but now you'd be looking for a p prime of less than 0.05. And again, mathematically, those things are equivalent, and I hope that's kind of clear in the presentation of the 2 formulas here. But it's important to know which adjustment your stats program is making so that you're kind of interpreting the p-values correctly when you're looking at either an adjusted alpha level and raw p-values, or you're looking at adjusted p-values and the original alpha level. So finally, right, we can adjust the alpha level of each post-hoc test in order to control the type 1 error rate overall. Once we've chosen our strategy, are we going to do pairwise comparisons or are we going to do simple effects tests, we can further make a decision about how we want to implement a correction from multiple comparisons. And on the kind of the far liberal side of the spectrum would be not making any correction. And sometimes that is an acceptable approach to take. A lot of the time, though, we're going to want to make some kind of adjustment for multiple comparisons. So we might do a Bonferroni correction, but like we said, that does tend to be very conservative. And there are far too many other types of corrections for me to put them all in this video. So I would need you to probably go and look at some of these things on your own and try to make an assessment about which is best for you. However, as a general piece of advice, the best adjustment to use depends on the number of tests that you're going to run and the relative cost of type 1 and type 2 errors. And the worse a type 1 or a false positive error is going to be, the more conservative you want to be. The worse a type 2 or a false negative error is going to be, the more liberal you want to be. Right? So you have to think about the balance of those 2 different types of errors in deciding if you want to be more liberal or be more conservative. However, you also want to commit to this plan in advance, right? So you want to really think about your problem before you run your analysis and you start doing these post-hoc tests. Because, although people might disagree about what the best strategy is or the best correction is, everyone would agree that you don't want to make this decision after the fact. You don't want to look at what gives you statistically significant results and then decide, yes, that's the post-hoc test that I want to run, right? You should be able to commit to an analysis plan up front and then interpret your data using that analysis plan. Don't analyze your data first and then poke around with different analyses until you find a post-hoc testing system that gives you the answer that you want. So I know that is still a little bit open-ended, but post-hoc tests just are a little bit open-ended. But in general, right, you want to pick a strategy, whether it's pairwise comparisons, simple effects tests, or something else. And you want to pick some method for correcting for multiple comparisons, deciding how liberal you want to be or how conservative you want to be based on the number of tests that you have to run and the relative costs of false negative to false positive errors.